So as we move to this unit of uniformly accelerated objects, or constant acceleration, we need to address one more type of motion, and this would be objects that are falling under the influence of gravity, or sometimes we call these free fall. So we want to do four things here. Relate the motion of a freely falling object to the uniform or the constant acceleration. We also need to realize that we are going to exclude air resistance. So we're going to say air resistance is neglected or it's absent when this object is dropped near the surface of the planet. And as we move through this, we're going to start with a historical perspective of free fall. So that takes us back to Galileo. I'm not going to read through this, and the Leaning Tower of Pisa. So you can read through this and kind of get a little historical perspective of where we were at one time during Aristotle's belief compared to where we are today once Galileo came up with his idea. Now, not only this, but I do have a clip here of the feather and hammer drop on the moon. This is an experiment that was done in 1971 by the Apollo 15 mission. So this is a good real experiment to show us that in the absence of air, which there is no atmosphere on the moon, they should hit the ground at the same time. You'll notice though, this film is not very clear because of the quality at that time. So it's just a good little video to watch. So when we talk about free fall acceleration, this is going to be due to the gravity on the nearest planet that the object is closest to. So most of the time, we're going to talk about acceleration due to gravity on Earth. At the surface of the Earth, the acceleration due to gravity is 9.81 meters per second each second. So that means, on my diagram here, if I drop something from rest, at the end of the first second, it should be going 9.81 meters per second. At the end of the second second, it should be going 19.6. And so you can see it's increasing by 9.8 every second its velocity. That's what this meters per second means. It's changing its velocity that much every second. Okay? Now, when we look at this, since it's a downward motion, down in physics is negative, we say acceleration due to gravity on Earth is a negative 9.81 meters per second each second. So this would be an example of a ball falling from rest under the influence of gravity. So we can see every second it increases its displacement because it's speeding up as it is falling. And so here's the graph. Here's a position versus time. Oh yes, it's a curved line because it's accelerating. Then there's the velocity versus time. This is falling downward. Down is negative and it's increasing in speed. And then the acceleration is constant and it's about a negative 10 roughly. So this is showing us that constant acceleration for something that is falling. So we're going to begin by looking at a problem that is a free fall problem and solve this graphically. So in the workbook, this is problem number 3 on page 124. It asks you to draw a diagram that represents this motion. The diagram that would represent this motion would be like a motion map, and then we will sketch the graphs for this also. So a motion map would look like this. It's starting from rest, and they told you that. And it's going to increase its speed as it falls. And we'll just say right there, it's going to hit the ground. And we want to know what is the velocity final here right before it hits the ground. That's what we want to know. Okay? So if I went and if I did a position versus time graph, wouldn't it look like this? So this would be 30 meters, I think the height was. Okay? If I did a velocity versus time graph for this situation, this is falling down, down is negative. It would look like this. Okay? And then if I did an acceleration versus time, we know anything in free fall, it's going to have this negative 9.81 meters per second each second. Okay, so those would be what the graphs would look like for us. Now, we want to go on these graphs and we want to label, what do we know? Well, this is the 30 meters that it falls, and since it's falling down, it's a negative 30. Okay, and I know that that is this area underneath that line. Okay, so it looks like it's a triangle. And then the other information I know is that the slope of this equals that negative 9.81 meters per second each second. Okay, and then that's where I graphed it over here. Okay, so that kind of gives us some of the information that we need to know for this problem. Now, we need to solve for this. They want us to know, or want to find out, how fast is it going right before it hits the ground? That's what we want to find out. Well, if I look at this problem graphically, don't I know that this area is the displacement, right? So it's a triangle. So the area of that triangle equals 1/2 base times the height. That area is the displacement, which equals 1/2 the time times the change in v. Okay, I'm just substituting in base is time, height is the change in v. The displacement is a negative 30 meters equals 1/2 time times change in v. I don't have the change in v and I don't have the time, so I need to get those from somewhere else. Well, there is something here. The area under a acceleration versus time graph represents the change in v. So this area right here represents the change in v, but I still don't have the time. I need to be able to get the time. And I don't have the change in v, but from previous problems that we've done, when we looked at how do we, our basic equations, didn't we have the acceleration average equals the change in v over t? So could I write the change in v as a different statement? Couldn't I write this as the change in v equals a times t? Oh, this equals the change in v. And the reason I want that is because I do have the acceleration, so I want to be able to use that value. So I could say the negative 30 meters equals 1/2 t times a times t, and I can simplify that. 30 meters equals 1/2 at squared. Okay, now I can substitute in here. Negative 30 meters equals 1/2 negative 9.81 meters per second each second times t squared. I'm going to do my math quick here. A negative 30 meters divided by a negative 4.905, and that's meters per second each second. Take the square root of that, that equals t. T equals 2.47 seconds. Oh, now I got the time. So this time, right here, I can put it up here. Now I know this time. 2.47 seconds. So the area, it's a rectangle, so the area of the acceleration versus time graph equals the change in v. So the change in v equals the base, which is acceleration, times the time, right? So we have a negative 9.81 meters per second each second times the time, which is 2.47 seconds. Time will cancel out. We would get a negative 24.2 meters per second. That's what the change in v is. Okay, so this is the change in v. Now, if I go back over here and look, isn't my velocity initial equal to 0? My velocity final, I don't know what that is. But when we look at the change in v, the change in v is always equal to the velocity final minus the velocity initial. When we do a change in anything, it's always final minus initial. So it looks like my change in v was 24.2 meters per second equals v final minus 0. Oh, isn't v final equal to 24.2 meters per second, a negative? It is. Now, in this problem, they just want to know how fast. How fast? They didn't ask the direction. They don't want, they just want the speed. So if we want the speed, all we do is we drop the sign. So the speed, how fast it is moving, really is 24.2 meters per second. So there's our answer right here. But we did it by solving for what was the change in velocity, because we know the initial velocity is 0 and the final velocity is what we're looking for. So this should help you solve those problems. I think it's number 3 and 8 on worksheet 5. And then we're going to get a packet that has more problems in it.